yours, David.
All right, thanks for the introduction, and thanks everyone for being here, and special thanks to the organizers for setting up this remote event. So I'm going to be telling you about some work done with my collaborators Haoxing Du, John Selby, and Matt Pusey on proving that the stabilizer subtheory has a unique non-contextual model. Everyone can hear me fine? See my screen and everything? Perfect. So the main results of this talk are going to be as follows. First of all, for any stabilizer subtheory in odd dimensions, there's a unique non-contextual model given by Gross's discrete Wigner function, or equivalently given by Spekkens' toy model. In even dimensions, every stabilizer subtheory we show is contextual. So this is just extending the well-known result that the qubit stabilizer subtheory is contextual. And the second main result of the talk is that generalized contextuality is a necessary resource for quantum computation in a particular model for quantum computation. So what is the stabilizer subtheory? Well, it's a strict subset of the states, transformations, and measurements in quantum theory. And it's particularly useful for studying quantum error correction, quantum information processing, quantum computation, quantum foundations. It's a really useful subtheory to consider because it has a lot of interesting structure. And practically, the reason it's interesting is because all the processes in this subtheory can be implemented fault tolerantly. And furthermore, if you inject some particular non-stabilizer resources, then you can promote the stabilizer subtheory to universal quantum computation. So you can build arbitrary quantum circuits. And this leads to a particular model called the state injection model for quantum computation. And it's one of the leading models for fault-tolerant quantum computation. Now, the stabilizer subtheory is often studied using quasi-probability distributions or quasi-probability representations. And these are kind of like ontological models, except the probabilities can go negative, so they're not real probabilities. So there's many examples of these, like Wigner functions, Gross's representation. There's a family of Gibbons-Hoffman-Wouters representations, and so on. And Gross's discrete representation, in particular, has found a lot of useful applications in studying quantum computation. And many of these were proven by the group at IQC. So for example, Gottesman and Nil have a famous theorem that every stabilizer subtheory can be efficiently simulated on a classical computer. And these guys extended that result to show that, in fact, an even broader subset of circuits beyond the stabilizer subtheory can also be simulated classically, namely those where all the processes are represented positively in Gross's representation. Furthermore, they showed that every state which is useful for magic state distillation has negativity in Gross's representation. And building on this result, they proved that every state that promotes the stabilizer subtheory to universal quantum computation via magic state distillation has to be co-conspec or contextual. And additionally, they showed that negativity in Gross's representation is a necessary resource for quantum computation. So there's all these interesting results related to negativity in Gross's representation. And foundationally, this raises a question. Because it's well known that negativity in one particular quasi-probability representation is not generally sufficient to establish that you have any non-classicality. Because even if there's negativity in the representation you're considering, somebody else might come along and find a representation that's positive for your entire theory or scenario, in which case you have a simple explanation for what's going on. So why is it that negativity in one particular representation, namely Gross's, happens to be associated to a strong form of non-classicality, like universal quantum computation? Surely this isn't some kind of coincidence. And in fact, this talk will give the answer to that question. It's because Gross's representation is the only possible classical representation of the stabilizer subtheory. What I mean by this is that it's the only positive quasi-probability representation. Every other quasi-probability representation has some negativity when representing the stabilizer subtheory. Equivalently, if you view the stabilizer subtheory as an operational theory, then Gross's representation gives the only non-contextual ontological model for that subtheory. And if you're interested in the relationship between positive quasi-probability representations and non-contextual ontological models, I think for a long time it's been understood that there's a close connection here, but we haven't really actually pinned down the precise connections until these two recent papers. So you should check them out if you're interested in understanding this connection better. But for now, I just want to focus on the fact that here I'm kind of conflating the existence of a classical explanation with the existence of a generalized non-contextual ontological model. And there's a long list of good reasons for doing this. So first of all, the existence of a generalized non-contextual model is equivalent to a quantum optics notion of classicality. And that's the notion on the previous slide, the existence of a positive quasi-probability representation. It's also equivalent to a notion of classicality that's independently motivated within the generalized probabilistic theory framework, the framework for GPTs. And namely, that notion of classicality is the ability to embed your GPT into a simplicial GPT. Generalized non-contextuality emerges in the classical limit studied by the quantum Darwinists. It's motivated by Leibniz's principle of the identity of indiscernibles, which is a principle for theory construction that has been particularly useful in the past, as evidenced by some of Einstein's best work. Furthermore, non-classicality, in this sense of generalized contextuality, subsumes other notions of non-classicality, like Koch-and-Specker contextuality, Bell non-locality, and anomalous weak values. And generalized contextuality is a resource for quantum computation, quantum communication, state discrimination, cloning, metrology. There's a long and growing list of things for which contextuality is a resource. So that's why we're taking generalized contextuality as our notion of classicality. And what this implies with our result is that in the setting of the odd-dimensional stabilizer subtheory, if you have some process which is represented negatively in Gross's representation, then there's no classical explanation for that process together with the stabilizer subtheory. So negativity of Gross's representation implies non-classicality. So to put this all graphically, how this relates to computation, we start from some known facts, some known connections between computation and negativity in Gross's representation. In this talk, I'll discuss how negativity in Gross's representation is linked to generalized contextuality, which then by transitivity forms a link between generalized contextuality and quantum computation. And this is an exact analogy to what Howard et al. Did in their Nature 2014 paper for Koch-and-Specker contextuality. So this is the paper, Contextuality Supplies the Magic for Quantum Computation. So what they did there was they proved a link between Gross negativity and Koch-and-Specker contextuality, which then again through this connection on the top here, proved a link between Koch-and-Specker contextuality and computation. We're going to do the same thing, but for generalized contextuality. Okay, so what is the stabilizer subtheory? Well, I'll start by defining it for a single system of dimension D. This is how I'll denote the computational basis. And I'll denote the dth root of unity by omega. And then I need to define for you the generalized Pauli operators on a system of dimension D. So there's a generalized X operator, which acts on the computational basis states just by incrementing them by 1 like this. It's kind of analogous to a position translation. And there's a generalized Z operator, which acts on the computational basis states by picking up a phase like this. So this is like a momentum translation. And once you have these defined, you can define the so-called Weyl operators. So a Weyl operator is indexed by an integer mod D, P, and another integer mod D, Q. And these are just labeling how many appearances of the X and Z operator are in the definition of this Wigner, this Weyl operator. So the Weyl operators are just Q-fold products of Q times P-fold products of Z. So you can think of it like shifting the position by Q and shifting the momentum by P. So these are kind of shift operators, if you like. And once you have these Weyl operators, it's easy to define the stabilizer subtheory. The states that are allowed in the stabilizer subtheory are the eigenstates of the Weyl operators. And the measurements are just projective measurements in the eigenbases of the Weyl operators. What about transformations? Well, the allowed transformations are called Clifford Unitaries, defined as the unitaries that preserve the Weyl operators. So if you take some Weyl operator here, indexed by P and Q, and you apply some unitary transformation to it, if you get something that's equal up to a phase to another Weyl operator, then U is said to be Clifford, and it's an allowed operation in the stabilizer subtheory. So that's pretty much all there is to it. Clearly, as I've defined things, this subtheory is closed under composition, and we furthermore close it under convex mixtures. And that defines the stabilizer subtheory for a single system of dimension d. If you have n systems of dimension d, then you do pretty much the same construction, but you don't start with Weil operators on a single system. You start with n-fold tensor products of Weil operators. And what Gross showed in his paper is that the stabilizer subtheory on n d-dimensional systems is not the same as the stabilizer subtheory on a single d to the n dimensional system. So this is what he called the multiparticle view. This is what he called the single particle view. And he showed that the single particle stabilizer subtheory is a strict subtheory of the multiparticle view, multiparticle stabilizer subtheory. And this is perfectly fine. It just means for a given dimension, there might be more than one valid stabilizer subtheory that can be studied. Okay, so as I mentioned, the stabilizer subtheory, it's often useful to study this or even all of quantum theory using a quasi-probability representation. So what are these? Well, as I said, they're kind of representations of quantum processes as stochastic processes on some sets. So it's kind of like taking your quantum processes on quantum systems and representing them as some kind of classical-like processes on classical systems, but they're not really stochastic or classical representations because the so-called probabilities can go negative. So they're not really valid probabilities. And we assume that all quasi-probability representations are diagram preserving in this talk. So what diagram preserving means is if I have some circuit here and I apply the representation, I try to find the representation of the circuit. If the representation map is diagram preserving, that means that we can equivalently just represent each individual component of the circuit and then wire them together in the same sense. And that will be the representation. So it's a very natural assumption to make. It's, for example, it says that this state in the quantum circuit is represented by a state in the quasi-probability representation. A transformation is represented by a transformation, and so on. And it's worth noting that most of the things that have been called quasi-probability representations in the past satisfy diagram preservation. The most successful ones do, like Wigner's representation or Gross's representation. But not everything that's ever been called a quasi-probability representation is of this sort. But we're going to assume this property. And what we show in this paper here is that every diagram preserving quasi-probability representation has a very strict mathematical structure and a very simple mathematical structure. If you're interested in this result, you should see Matt Pusey's recorded talk at this conference. And this result is a very useful structure theorem. And in fact, it's sort of the big first step in proving the result of this talk. So this talk is kind of an example of how useful this structure theorem is. So what is the structure of every diagram preserving quasi-probability representation? Well, it's as follows. You start by picking a basis of trace one Hermitian operators for the given Hilbert space. And then you compute the unique dual basis satisfying this orthonormality condition. So the dual basis is some set of operators D indexed by lambda. And then to compute the representation of the states in the representation, you have a real vector indexed by lambda for each quantum state, and you compute that vector by taking the trace of the quantum state with the elements of the dual basis. The representation of effects is given by tracing the effects with the elements of the original basis and getting a real vector, a vector of real values again. And transformations are represented by matrices with two indices obtained by tracing the action of that channel on the basis elements traced with the dual elements. And so every diagram preserving quasi-probability representation can be constructed in this manner. And I should note that there's some additional caveats. In particular, we prove this result for tomographically local scenarios and for prepare transform measure scenarios. So we're not sure if an analogous result holds for simple prepare measure scenarios. Okay. So for a quasi-probability representation to be meaningful, it better reproduce the quantum predictions. So what I mean by that, for example, if we have some closed quantum circuit like this, well, the probabilities in this circuit are given by quantum theory to just be the Born rule, like this. So this equals this. And then if we represent this scenario, so I'm, as before, I'm graphically denoting the application of the representation map by this kind of shaded box. So the representation of this quantum circuit by diagram preservation is equal to the representation of each component individually and then wired together. So each component here is a process within the process theory of substochastic matrices. So this is like a vector of real values, a matrix that acts on it, and so on. And in particular, composition in this process theory is just given by matrix multiplication like this. So reproducing the quantum predictions means that this quantum probability should be equal to this probability computed in the representation here. So Gross's representation in particular, it's an instance of a diagram preserving quasi-probability representation, which means it's constructed exactly as on the slide that I mentioned previously. And the particular set of operators that Gross used to define his representation is defined as follows. It's some particular linear combination of the Weil operators that I defined for you earlier with some complicated looking face up front. And you can see that these operators are indexed by an integer mod d p and an integer mod d q. So these are often called phase point operators or phase space point operators, because you can think of these indices on these operators as points in a phase space. So for qubits, for example, we have a 3x3 phase space. Q can take 3 possible values, P can take 3 possible values. So we have 9 such operators and 1 for each point in this kind of phase space. And if you compute the unique dual to this basis, you find that it is itself. So this is a self-dual representation. And once you have this set of operators and its dual, then you just go ahead and you compute the representations of the things you're interested in, which here are stabilizer states, transformations, and measurements. So the representation of a stabilizer state is given as always just by tracing with these elements of the basis or the dual basis. And what you get then is some real numbers indexed by P and Q. And it turns out that these real numbers are always between 0 and 1. In fact, this is a valid probability distribution over the phase space. So here we see there's 12 pure states in the stabilizer subtheory for qubit. And here's their representation and Gross's representation. So you've got these probability distributions over phase space where there's exactly 3 non-zero points, each of which takes value 1/3, and they always lie in a kind of line in phase space mod d. And you can have representations of multiparticle states. So here's a maximally entangled stabilizer state of 2 qubits. And this is what it looks like as a probability distribution over the phase space. You can see there's kind of a high degree of correlation between the positions and the momenta of one particle and those of the second particle. What about the representation of unitaries? Well, as always, we just apply the unitary to elements of the basis and take a trace with the elements of the dual basis. And we get a matrix like this, which you can write down its action on the phase space. And you can picture that diagrammatically as well. And here's what it looks like for some kind of entangling operation of 2 systems. None of these details are too important. What I want to note is these are valid stochastic processes on the phase space. In general, they didn't have to be. This is a quasi-probability representation. These values could go negative and then they wouldn't have a simple interpretation. Like here we have a nice permutation on the phase space. In fact, these turn out to always be symplectic permutations. But the main point for our purposes is that Gross's representation goes positive for all stabilizer processes. And furthermore, the result that we prove in this paper is that in odd dimensions, his representation is the only one that's positive for all the stabilizer processes. So Gross's representation is the unique positive quasi-probability representation that satisfies diagram preservation for every stabilizer subtheory in odd dimensions. This includes the single particle subtheories and the multi-particle subtheories that I mentioned earlier. And an equivalent way of stating this result is that there's a unique non-contextual ontological model for the stabilizer subtheory. And recall that you can think of this as Gross's representation, or you can think of it as Spekkens toy theory. Either way, this is the unique representation. These two are equivalent in odd dimensions. And in even dimensions, we show that there's no positive quasi-probability representation for any stabilizer subtheory, not just for qubits, but for any even dimensional stabilizer subtheory, single or multi-particle. Equivalently, there's no non-contextual ontological model. So you can find proofs of contextuality in any of these subtheories. So there's a unique classical explanation of the stabilizer subtheory. And this kind of was amazing to us. You start with this principle of non-contextuality, which is this kind of high-level abstract principle, and it's not really clear what the scope of possible non-contextual ontological models is. It seems like there might be many possible different kinds of models and many possible ontic state spaces for each model and so on. But in fact, we were able to prove here that this principle is strong enough to single out a unique ontology. So if the world really were described by the stabilizer subtheory, then this would be the only way of understanding it in a classical way. The first step in proving this result, as I mentioned earlier, was to use this structure theorem that really constrains the space of representations. In particular, it shows that the number of ontic states in any non-contextual ontological model under the assumptions we used has to be exactly equal to the dimension of the GPT state space, which is a really constraining property. So in the setting of the odd dimensional stabilizer subtheory, negativity of Gross's representation implies non-classicality. And so I'll just remind you of this picture we had earlier. So there's these known connections between negativity and Gross's representation and quantum computation. Our result proves that if you have some process which is represented negatively in Gross's representation, then that process, together with the stabilizer subtheory, must be able to form a proof of contextuality. And then it follows that there's connections between contextuality and computation, which is what I'm going to talk about next. But first, I want to have a one-slide digression on pointing out that Gross, in his original paper, actually proved a uniqueness theorem of his own. Namely, he proved that his representation was the only representation among a particular family of representations that had been previously studied by Gibbons, Hoffman, and Wouters. Among this family, Gross's representation is the only one that has an elegant mathematical property known as Clifford covariance, which basically just says that the transformations in the stabilizer subtheory are represented as symplectic functions on the phase space. So there's a number of advantages of our uniqueness result over Gross's. First and most importantly, we prove that it's unique in the sense of being the only generalized non-contextual model, and generalized non-contextuality is a notion of classicality, whereas covariance is not. So our result is really linking Gross's representation to a kind of important foundational concept, whereas Clifford covariance is more of an interesting mathematical property and an elegant property, but it's not linked to deeper foundational notions as far as I'm aware. Also, Gross's result requires two ad hoc mathematical assumptions. So he assumed that the representations are on a d by d phase space, and he assumed something about the way that marginal probabilities are represented. Neither of these assumptions is empirically verifiable, nor kind of conceptually motivated. They're just useful mathematical properties. And in our approach, we don't need these assumptions. We derive them from the assumption of non-contextuality. And finally, Gross's uniqueness result holds only for odd prime dimensions, while ours holds for all odd dimensions. So we've given a complete characterization of the classicality or the non-classicality of the stabilizer, of every stabilizer subtheory in every dimension. Okay, so returning back to quantum computation, any state, here's a well-known fact that was, I think, proven, well, I forget who proved it. It might have been the guys at IQC, or maybe it predates them. But the fact is, any state which promotes the stabilizer subtheory to universal quantum computation must have negativity in its Gross's representation. Now, what Howard et al. Showed in their Nature paper was negativity in Gross's representation of a state implies that you can find a state-dependent proof of Koch-Specker contextuality using that state. And if you put these two results together, it says that negativity in Gross's, it says that Koch-Specker contextuality is a necessary resource for universal quantum computation. So what we've just discussed in this talk is negativity in Gross's representation of a state also implies generalized contextuality. That was our main result. So if you put our result together with this fact up here, you get that generalized contextuality, like Koch-Specker contextuality, is a necessary resource for universal quantum computation in this model. And so that's necessity. What about sufficiency? Is generalized contextuality sufficient for computation? Well, it's obviously not sufficient, at least if you don't add some caveats. Maybe it would be sufficient if you had like a certain quantitative amount, but for that sort of thing, you'd need a resource theory. So at least without caveats, it's not sufficient. And this is clear by example. So if you look at the even dimensional stabilizer subtheory, it's contextual, but by the Gottesman-Nil theorem, it's efficiently simulatable. So I'll just close with a kind of an additional fact about sufficiency that we prove in our paper. I'm not sure how important it is, but it's maybe kind of interesting. So it's known that every non-stabilizer pure state and every non-stabilizer unitary promotes the stabilizer subtheory to universality. And it's also known that every non-stabilizer pure state has a negative gross representation. And what we proved in our paper is that every non-stabilizer unitary has a negative gross representation. If you put these two results together, you find that for pure states and unitaries, negativity in Gross's representation is a sufficient condition for promoting to universal quantum computation. So that's kind of cute. Admittedly, the much more interesting question is what happens for mixed states and for arbitrary quantum channels. That's kind of the fundamental question that everyone's been asking since the Nature paper by Howard et al. And we don't have an answer to that yet, but we're hopeful that the results and the techniques in this work of ours will be helpful for answering that question. That's all I have time to say. Thanks for listening. Here are the archive links for the most relevant papers to this talk if you're interested.
Thank you, David Schmid.